This lesson we're going to cover some of the functions that we haven't gone over too much, that being the square root function and the semicircle function. We'll start off with the square root function being y equals the square root of x. They want us to substitute in the values so that we can kind of make a rough sketch. So let's make a table of x, y values. If x was 0, the square root of 0 would be 0. If x is 1, the square root of 1 is 1. If x is 4, the square root of 4 is 2. If x is 9, the square root of 9 is 3. So that gives you a rough sketch right here. 4, 2, 9, 3 of this graph right there. It starts to level out a little bit, but it'll continue growing for the entirety of the graph. If I was to use let's use a slightly darker color for that to really show it. So that's what that guy looks like. That's what our function square root of x looks like. And they're asking some questions about this. The characteristics of this function are, well, our domain. Well, if you see I start at 0, what happens if I go to -1? Well, if I put a negative under a root, that's a no-go. We're not allowed to do that in the real plane of numbers. Imaginary numbers, yes, but as far as the real numbers are concerned, which we're plotting on, can't do anything about that. So our smallest value for our domain is going to be 0, and that is included, so that's why we have a bracket, all the way to infinity. It's just going to keep going on forever. And that's as a parentheses because infinity is not a real number that we include. Similarly, our range is going to go from a y value of 0. Can't go less than that because there's no way to make this negative. And it's going to go continuously up towards infinite values of y. So they're identical. Is this a function? Well, does it pass the vertical line test? Sure does, so that is a function. And is it one-to-one? Does it pass the horizontal line test? Yeah, it passes horizontal line test. And because of that, because we know that it passes the horizontal line test, we know that its inverse function, which will look like this. Oops. His inverse function will also be a function. He is going to pass the vertical line test. With all of our transformations that we've done in the past, we know some pretty concrete rules. We'll take our parent function, we'll modify the graph in relation to the things that we're adding or subtracting on the outside, adding or subtracting on the inside, multiplying, so on and so forth. So let's begin with our parent graph. So we know it's this point, and this point as our general shape. And when I am inside the function, that means I'm dealing with things on the horizontal axis. So I'm going to shift all of my points to the left 2. It's the opposite of the sign. So this means that all my points will go left 2. And because this right here, this -3 is on the outside, that means that all the points are going to shift down 3. So everything's going to go to the left 2 and down 3. So this point will go there. This point will go here. This point goes there. And this point will go there. So he will look like that. And I overshot the points a little bit, but as long as you can see and understand the translational effects that are occurring. Example 2, now if we have a stretch factor in, so we'll take our standard points. Get something a little bit darker for this. This stretch factor means my y is just going to become 4 times larger in every instance. So instead of being a 1 here, it would be a 4 here. Instead of being a 2 here, it would be an 8 there, so on and so forth. This guy is just going to grow much taller, much faster. So on a quiz or test, you should be able to identify that the 4 is just making it elongated. It's making it taller. This is where it gets really tricky. So there's a negative inside. If there was a negative on the outside, it'd be flipping it across the x-axis. We know that. But there's a negative on the inside. That means it's going to be flipping it on the horizontal axis. So first thing we should do is pull out this negative. If we pull out this negative, we get x plus 3. Because I pulled the negative out of both the x and the 3. So this means that from our parent function, which one there, there, and there, from our parent function, I'm going to shift to the left 3 up 2, and I'm going to flip it across the y-axis. So instead of opening to the right, it's going to open to the left. So that means that this point would still be that, or sorry, this point is going to be shifted to the left 3 and up 2. So let's go that there. And the points are now, instead of going right 1, up 1, right 4, up 2, it's going to be left 1, up 1, left 4, up 2. Like that. So you got to be tricky. You got to be careful for this trick. If I put a negative on the inside of the root, you're going to have to pull it out of both numbers so that we can see that, oh, okay, x plus 3, that means that I'm shifting all of my points to the left 3. Be a very common mistake to say, oh, this shifts to the right 3 and flips. No, 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 we've got to pull out the negative from both. As I was saying before, with the negative on the outside, we're going to flip this over the x-axis. So before we were opening up and to the right, now we're going to open down and to the right. But on top of that, we're going to have a, let's draw our parent function right here. He's also going to shift up 5. So this will be 1, 2, 3, 4, 5 up there, and he's going to go, instead of going to the right 1, up 1, it will be down 1, right 1, over 4, down 2, over 9, down 3. Like so. Now we're going to be asked to identify what's happening to these graphs. So this, relative to our parent function, which is the root function, we are going to the right 2 and up 1, and we are, instead of opening to the right, we're opening to the left. So if you're opening to the left, we've got a negative under the root. Because we have shifted to the right 2, this is going to be x minus 2. And because we've shifted up 1 outside of the function, will be a 1. So this is our f of x. This one, we've just flipped it over the x-axis. So instead of looking like that and opening up and to the right, he just flipped upside down. So we know from the previous examples, this is just the negative square root of x. And that covers all of our square root functions. Now let's talk about semicircles. Consider the equation of a circle centered at the origin of radius r. So if we had a circle centered at the origin with radius r, we know that the function is x squared plus y squared equals r squared. So if I had this for a circle that looks something like this, I could ask, is this a function? And I know right off the bat, because it fails the vertical line test, it's not a function. Is there any way that I could potentially break this down so that I would have a top part of the circle and a bottom part of the circle? Yeah, it is. And if I cut those in half, I'm going to make two semicircles. So what we'll do is we'll take the top part of our circle, make that one function, the bottom part of a circle, and we'll make that another function, and then we'll have two perfectly viable functions. So how do I solve for that? Well, in terms of y, let's always solve in terms of y. Subtract x squared from both sides. So I get y squared equals r squared minus x squared. And then I will square root both sides and get y equals plus or minus, because anytime you square root you got to do plus or minus, r squared minus x squared. And this is where we break it up into our top and bottom. If we use the positive, that's going to be the top part of our semicircle. If I use the negative, that's going to be the bottom part right down here. So identifying really quickly off the bat the plus or minus and which one we're using is a nifty trick to just say, oh, that's the graph that I'm looking for. So we got to remember this is r squared, r squared. If you see a square root of r squared minus x squared, be on the lookout for a semicircle. So sketch the transformed semicircle, give the domain and range, and give a word description of the transformation. So this is our r squared. So if our r squared is 9, that means our r is 3. 1, 2, 3. 1, 2, 3. Question is this our positive or negative? Is our top or bottom? Because this is a positive 2, it's going to be the top points. Now this 2 is a stretch factor, similar to what we did with the square root function. We're just going to stretch it up. We're going to stretch it up a little bit by twofold. So it will grow up twice as fast. So that means that instead of 3 being our radius, it's going to, in the y direction, it's going to double and become 6. So this is going to look like so. What is the domain of this semicircle? Well, it's all the points from, you can look at the graph, from -3 to +3, and both of those are included, so we got brackets. What's our range? Well, the smallest point on this graph in the y coordinate is 0, and the tallest is 6. Give the domain and range and the word description of the transformation. Stretch by a factor of 2. So we'll say stretch, vertical, it's a vertical stretch, by 2. This guy negative, our next function, example 8, -25 minus x squared. Square root of 25 minus x squared. This is our r squared equals 25. So that means our r is going to be 5. The negative means that it is going to open down. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And he would look like so. The only reason I'm doing dashed points is because it's easier for me to draw out a curve like that. So that's the bottom semicircle we'd be looking for. Okay, now for these next examples, we're going to have to be identifying what's happening, what transformation has occurred. So let's look for the center of this semicircle. Looks like this center is at -3, -3. And our radius is 1, 2, 3, 4, 5. So if I know that my function is going to be plus or minus the square root of r squared minus x squared, my r squared, if my r is 5, my r squared should be 25. Now I've shifted to the left 2, so you know that's inside the function. So instead of being minus x squared, this is going to be minus x, because I'm going to the left 3 plus 3 squared. So we've replaced the x plus 3 with that. And because I've gone down 3 outside the function, we're going to have minus 3. Now this is going to be the bottom part of the semicircle, so we're going to take our negative. This is our final equation. Negative square root of 25 minus x plus 3 squared minus 3. That seems awfully complicated, but if you break it down piece by piece, you know that you've taken your parent function, you've taken the negative version of the semicircle, you've shifted to the left 3 and down 3. This one, let's look at our center. Our center is at 0, negative 2. My radius in my x direction is 1, 2, 3, 4, 5. Strangely though, my radius in the y direction is 10. So to go from 5 to 2, it looks like there's a vertical stretch of 2. And we know that's just going to be a coefficient on our function. So that means that our function will be y plus or minus, let's do our vertical stretch, so 2. And because it's the positive semicircle, we're going to use the positive 2 and not the negative 2. Square root of our r is 5, so our r squared is 25, minus x squared, and this is not replaced by anything because we haven't shifted left to right anything. But because the point has gone down 2, outside the function we will subtract 2. So, complicated formulas at first glance, but if you apply the same transformations that you're accustomed to, you should be all right.